just so nobody, oh, he's not even there. Well, I mean, obviously me talking will be an indicator that I'm here. Ha 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 ha. Okay, so here we go. Today is Wednesday the 9th. This is in addition to it being Wednesday the 9th. This is our last day of new material for the exam. So on Friday, what we're going to do is I'm going to run through some practice problems and give you some pointers on things to study, things to look at with respect to your learning objectives and everything like that. So today what we're talking about is molecules with lone pairs of electrons and drawing them. Now, what I will on Friday, one of the things that I'll bring back is I'll bring up molecules with lone pairs of electrons. This is modification from and then molecules without. So I'm sorry, today is without. Oh my gosh, what happened to my text? Looks like I'm writing with a crayon. Out. There we go. Without lone pairs of electrons. So there we go. So we're drawing molecules without lone pairs of electrons. On Friday, we're going to be going through some of these, but we'll also be identifying the shapes of those. Is this a bent? Is this a tetrahedral molecule? What is this? What's the better term for the geometry? But at any rate, just as a little bit of a refresher, we've got to know how many valence electrons an element has, how many valence electrons any particular atom has. And so if we've got, group one, they're going to have one valence electron, group two, two valence electrons, group three, remember the periodic table, it looks like this. This is group one, two. Over here is 3, 4, 5, 6, 7, and 8. So that's basically our structure of our periodic table. So that means that these are right here. So keeping this in mind is going to be very helpful. As is always the case, you're going to have a periodic table on your exam, so you can use that as a reference. Now, what I've got planned for today is basically going through the process of drawing a total of 4 different molecules. So what we've got to do is we have to identify all the atoms, all of those electrons, and then find the central atom. Draw those atoms adjacent to your central atom or outside of your central atom, and then connect them with one line to represent 2 electrons or 2 lines to represent 4 electrons. Place all the other electrons until you reach your total, and then try to get each element to have a complete octet if it needs an octet, or as long as it doesn't exceed the octet. Now, we're also going to add double and triple bonds as needed. So if we start out with CH4, I like to start with this. We started with the last time. This is a central atom that doesn't have a lone pair of electrons. We've got 4 electrons around carbon, 4 electrons total that hydrogen brings in. So we've got a grand total of 8 electrons to draw. So our central atom is going to be carbon, H, 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 H. Hydrogen wants to have 2 electrons. It's got them. Carbon wants to have 8 electrons. It's got them. So we're good there. Simple, straightforward. Okay. Now, as an example of something that would not work is if you were to see CH3 as an alternative. Well, let's see. CH3. Is this a structure? Is this a complete structure? Well, carbon's bringing in 4 electrons. Each of these hydrogens is bringing in 3 electrons. So we've got a total of 7 electrons to draw. C, H, H, H. This accounts for 6 of our electrons. And then we'd have this, a single electron. Now, an important thing to know is that this would make what's known as a radical. Now, this isn't a term that you need to know for this class, but in the event that you ever hear about, free radical formation, that's something that happens in your body. That's something that's just kind of a natural part of life. Um, this is basically not good because what this is going to want to do is this electron is going to want to pair up with something else. And so it's going to want to find something to make a bond with. But in terms of drawing a structure, that's it. It's just that this structure is not really a possible structure to form. So then let's go ahead and let's look at this. SF6. Okay, so add to the chat somebody how many valence electrons sulfur brings in. And then somebody else add, okay, so we got 6 valence electrons. How about fluorine? F. Great. So we've got 6 times 7 because there's 6 of them. So that's going to give us 42 electrons. And then we got these other 6. So we're at 48 total electrons. Seems like a lot. Okay. Now, which of these elements is farthest to the left on the periodic table? That's our first step in finding our central atom. Farthest left, the other left. Sulfur. Okay. Now, we've got fluorine that we're going to basically throw all around our sulfur, 5 and 6. Okay. Have we drawn all our atoms? We have. Okay. Now, what we want to do is we want to start out by drawing a single bond to all of these fluorines. Okay, so that would be 6 bonds. Each one of those bonds corresponds to how many electrons?
The reason I highlighted these filters here at the bottom is
2. So we've got 6 times 2. We're looking at 12 electrons total. Okay, so we have 48. So I'm going to start my tally over here. 48 minus 12. And you're down to 36 remaining electrons. Now, before I do that, though, are there some elements that can exceed the octet? Basically, have more than 8 electrons around them.
I did something, yes, I did. I'm clicking around. There we go. Yeah, I got it. Now,
Absolutely, there are some. And just as there are some that can exceed the octet, there are some that don't need to reach an octet. So there are some that will have less than 8 electrons around them. But let's see what this gives us. Now, it might be helpful for you to think anytime I see a fluorine with a single bond, fluorine with a single bond will require 6 E around it. Another way, how could I take this and add this to the chat, or you can say it aloud if you'd like. How could I translate that to, instead of saying 6 electrons, talk about lone pairs of electrons? Perfect. Yeah, I can say that this is the same as 3 lone pairs. So a fluorine with a single bond is going to have 3 lone pairs of electrons. Boom, 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 boom. Okay. So, I mean, we can do the math. If there are 6 like that, there's 1, 2, 3, 4. How many electrons am I going to ultimately draw in total around all of my fluorines? Not counting my single bonds, because I've already accounted for those. 36. How many did I have left to draw? 36. So 36 minus 36, 0. So this is an example of a molecule that can exceed, or that has one atom that exceeds the octet. And that's just fine. Now, SF6, we had a total of 48 electrons to draw. How many lone pairs of electrons does my central atom have? My sulfur. How many lone pairs does sulfur have?
two things happening at the same time. The lead does choose a category for the thread when they do that wrap up. However, that data is
None.
not used for this
What?
purpose. This,
Sulfur?
dashboard utilizes
I think that
AI.
that was supposed to be none. So yeah, it has none. That sulfur has no lone pairs. Does it, however, have bonded pairs or shared pairs of electrons? It does, because each and every one of these single bonds is a shared pair of electrons. Now, next up,
So these
okay,
categories are not
BF3. Go ahead and add to the chat. Give me my valence numbers or valence electrons for boron and then for fluorine. Fluorine's 7 again, so 3 times 7 is 21. Boron is 3. Okay, so I got a total of 24 electrons.
categories can be
All right.
added.
So which one of my elements is farthest to the left? Boron. Group 3. Now that boron is going to have, let's see, 1, 2, 3. That corresponds to, let's see, 24 electrons, keeping my tally. I've drawn 3 single bonds, so that would be a total of 6 electrons. So I've got 18 electrons left to draw. Or sorry, yeah, 18 electrons left to draw. Again, single bonded fluorines. Each of those is going to have how many electrons, or how many lone pairs is it going to have? Each fluorine is going to have how many lone pairs?
Yes, it is in peer to peer. I just posted it there. And you
Great,
did get an
perfect.
email yesterday.
So that would look like this.
You can bookmark it, as it's updated, the link should be updated.
So that accounts for my, well, 3 lone pairs around 3 atoms. That's going to be 18 electrons. We're down at 0. No lone pairs of electrons around my central atom. Each fluorine has 3 lone pairs. I've drawn all 24 of my electrons. Now, my last model, we're switching it up a little bit. One of the big differences between what we were just looking at and what we're looking at now is how many valence electrons does phosphorus have? 5. Okay. How many valence electrons does chlorine have?
That's a really good question.
7. So 5 times 7 equals, what are we looking at? 35 plus these 5. We're looking at 40 electrons. Now, one of the things that I think is helpful to think about is, well, where is phosphorus on the periodic table? And where is one of the molecules that we looked at previously? We looked at sulfur, SF6, and now we're looking at PCl5. Well, let's go ahead and jump back. Chlorine effectively is the same in some respects in terms of bonding as fluorine. They're both examples of halogens. We have 40 electrons to draw. Our central atom, P, 1, 2, 3, 4, 5, Cl, 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 and Cl. We've got 5 bonded pairs of electrons. So 5 times 2 is 10 electrons. We had 40 to draw total. So 40 minus 10, we're at 30 electrons. Okay. When we talked about fluorine, fluorine had 6 electrons or 3 lone pairs of electrons. We've got 5 chlorines. So 5 times 6 is 30. We're back to 0. Now, what I want you to recognize and appreciate about all of this is that there's a pretty simple and straightforward process. You just kind of follow these rules. definitely are instances where it can get more complicated. We're not going to get into those examples because that's something that you would do in like an organic chemistry class, and that's not what we're taking. So if you think about a process for basically trying to clear this,
Health and other categories.
and then we're going to go back.
This is not the exact question that you asked, but, the answer.
If we're thinking about like the octet rule, that's
Here, so, you'll notice there's a category called OOO.
well, carbon likes to have a complete octet and does so by making 4 bonds. Phosphorus, sulfur, those are 2 elements that, well, they can exceed octet.
And being able to dig into those and maybe find a.
So if you wanted to, you could kind of think about it as basically carbon. Here, I'm gonna draw a little box around it. From carbon to silicon, those are things that I'm going to draw happy with an octet and will not exceed the octet, or the likelihood that they exceed is super low.
Yes, yes.
Phosphorus and sulfur, they can exceed.
Yes,
Does that mean that they absolutely do? No, it doesn't. But it means that they can exceed the octet. Carbon, as an example, will basically never exceed the octet. Boron doesn't need the octet. Now, as an example, or as another example molecule,
Yeah, is it because escalation?
if we talk about, let's say, let's go ahead and I'm going to jump ahead a little bit. So these were the molecules that I really wanted you guys to get your greatest familiarity with. Now I'm going to add some more. Scribble that out. Let's talk about carbon monoxide and carbon dioxide. In both of these cases, which element is farthest to the left on the periodic table? Carbon. Okay. We know that in both cases, carbon brings in 4 electrons. 4 electrons.
Well,
Oxygen brings in how many?
Yes, so.
Valence electrons, that is.
So thank you so much. We will take all of that into consideration. We've got a brainstorming session on renaming that's ongoing.
6. So 2 times 6 here equals 12. So carbon dioxide, we've got 16 electrons to draw. And carbon monoxide, we've got 10 electrons to draw. Now, this number, these 2 numbers, are your total number of valence electrons. Okay. Now, farthest to the left in both cases is carbon. So that's going to be our central atom. But when you look at a molecule like CO, there's not really a central atom. Carbon to oxygen, done. Okay. Now, CO2, done. Now, if we want them both to have a complete octet, what I'm going to do is I'm going to start with carbon monoxide. I'm going to give lone pairs of electrons to carbon and then lone pairs of electrons to oxygen. Okay. In this structure, how many electrons in total have I drawn?
Yes, I think, well, so ultimately the same is, is in this dashboard, it's just presented in 3 different. And so depending on
You're absolutely right, Kevin. 14 electrons, because here's 2, 2, 2, 2, 2, 2, 2. Okay, so this is 14 electrons. Now, a fair question there is, Do we have that many valence electrons to draw?
Here and download it this way.
The answer is, I mean, we got to compare
This page shows
the number that the total number of valence electrons that we could draw versus how many that we did draw. When those two numbers are out of sync,
your team, like, oh, my team is mostly asking.
we can only conclude that, well, this structure right here is wrong. Does that make sense? Because we didn't have 14 valence electrons to draw, we only had 10. So then, if that's wrong, does anyone have a proposal on what we can do?
So if you're looking at eventually all of our, majority or of our
And I'll give you a little bit of a hint.
then this will only be functional if we get that data.
You can share electrons between two different atoms.
Pilots going at the same time, lots of balls in the air, but
So I like it. Remove a lone pair. Okay. So let's go ahead and do this. See.
Oh, yes, I said that at the beginning, my
Okay, so we're going to use this. Josiah, love that idea of removing a pair of electrons. This structure right here, I have 12 electrons in it. Okay. Now that gets us closer to our 10, but it's kind of like one step forward was that we got closer to 10 electrons, but one step backwards in that now this carbon, it doesn't have a complete octet.
Yeah.
So when you remove a pair of electrons, and actually, you know what? I'm going to remove that pair as well. What we can do is now I've got 10 electrons there. If I add a double bond or add another bond between them, okay? So now what I've got is how many electrons? 1, 2, there's 2, 4, 6, 8, 10, 12. Okay, that's kind of crazy. I removed 4 electrons, but then put a double bond in. Okay, so that double bond represents exactly. So what I can do with this is I'm going to go ahead and add, I'm going to have this structure kind of evolve, and I'm going to remove another pair of electrons because this is 12 electrons right here. I'm going to make this a molecule with a triple bond.
But like the top 20%.
And whenever I do that, I've got 2,
there we go.
4, 6, 8, 10. So I've got 10 electrons in this structure, this done. There we go. My triple bonded carbon to oxygen. So I've got 10 electrons there. So this was the number that I could possibly draw. So if we've got a vote between structure A, B, and C, which one do you think is correct? A, B, or C?
I click here on facts topics.
Perfect. I love it. C.
Most of the
now
questions have been categorized as related.
I'm going to give you a minute to look at our carbon dioxide structure.
That makes sense. You're going to see those sort of.
Try to draw that one out yourself. And then in about 30 seconds, we're going to walk through it. And, just look at your own structure and look at the one that I put together.
Side and answering questions and say, a minute, so something that may immediately seem like more complex might not.
Okay. So we've got our kind of evolution. I always like to draw every single electron. Make everything have a complete octet. So this would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I got 20 electrons here. And I count it off like that just because it makes more sense to me to kind of keep track of it. And I'll write two by every one of those. Okay, so now what I need to do is I need to get from 20 down to 16. And so I know that I probably need to throw a double bond in there. So I'll throw one double bond in. Then, oh, boom, 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 boom. Okay, so that oxygen has a complete octet. Carbon has a complete octet. It sees 8 electrons. 8 electrons. Josiah, okay. Thank you very much. That's awesome that you put it into text form. Um, and I love that. So let's use your model because this one that I just drew in has 2, 4, 6, 8, 10, 12, 14, 16, 18, 18 electrons. Josiah is proposing a structure where we've got double bonds between our carbon and our oxygen. Spot on. And this is just the limitation of your keyboard. I know that you got this right. Each oxygen is going to have two lone pairs of electrons. There's not really I mean, a colon is a great job with your lone pairs of electrons, but there unfortunately no keyboard has a two lone pairs of electrons that you can input. So this is going to get us to our 16 electrons. So this structure right here. Okay, well, this was kind of where I wanted to go for today, just walking through some of the process of drawing molecules. Um, Tomorrow, or sorry, on Friday, I'll have the exam done. And so I'll be able to answer questions about that and go through a little bit of a review with a PowerPoint on, here's things that I want you to be able to do and talk about different like tiers of questions. This is a lower tier question, the higher and highest tier question. Um, is there a study guide? I think I'm fairly certain that I have the learning objectives. I'll check on that. Since you're asking, I'm guessing that I didn't publish that page but I will definitely give you more materials that you can use to study for this exam. Um, so that's kind of where I wanted to go with today's material. I'm going to have two quizzes that are posted today at 11 a.m. and those will close on Sunday night at 11 p.m. Just as kind of like last little things to look at. In terms of a calculator, I don't really think that there's a strong need for one. Um, I'll have a better answer for that, like kind of the extent of the calculator that you need on Friday, um, after I finish writing the exam. But yeah, so there we are. Then I think what I'm going to do is if there's anyone who's willing to hang around, and I really only need one person for this, but if there's any one person who's willing to hang around for a minute to help me go through some of my issues with Top Hat, I want to see, like, if you're having issues, like if you've been dropped from Top Hat or something like that, please hang around. You can send me a separate message. And yes, you will be able to use a note card. Okay, cool. I've got somebody who's willing to help me out with the Top Hat. I sent you. Yes, I'm still working through Top Hat, and I'm going to make sure that everyone has the points that they are owed. I'm guessing that there's some sort of, or I don't know exactly what the issue is, but for some reason, some people are like being dropped.